Welcome to the Deep Dive, where we transform your sources into clear, engaging insights. Today, we're plunging into, well, a really specific corner of number theory, OEIS sequence A000322, the Pentanacci numbers. Now, this is part of our series for, number theory students, and we're looking at what makes the sequence stand out, especially among other higher-order Fibonacci types. What's really interesting, I think, is how it starts. A lot of these generalized sequences begin with zeros, but not this one.
Exactly. That's the core of it today, really. It's a perfect example for you listening of how just changing those initial numbers,
Right.
even with the exact same recurrence rule, can lead to, well, mathematically distinct sequences. It really makes you think about definitions in math, doesn't it?
It does. Okay, so let's unpack this sequence, A000322. Fundamentally, it's like other Pentanacci numbers, right? Each term is the sum of the 5 before it.
That's the recurrence, yes. AN1 plus AN2 plus AN3 plus AN4 plus AN5. That part's standard for any Pentanacci sequence. But for A000322, the crucial bit, the definition almost, is those starting values. It kicks off with A00, A1, A2, A1, A3, 1, and 1, all ones.
All ones, okay.
Which then generates the sequence 1, 1, 1, 1, then 5, then 9, 17, 33, 65, and it keeps going like that.
Right. And this is where it gets, well, potentially confusing for students, because if you just search Pentanacci numbers, you might bump into another common one, OEIS A001591.
That's probably the more commonly cited one in some contexts.
And that one starts completely differently, doesn't it?
Completely. It starts 00001. Same recurrence rule, some of the previous 5, but those initial zeros make it generate a totally different set of numbers initially.
So the takeaway here is that the term Pentanacci can be a bit ambiguous. You need the OEIS number or the starting conditions to be sure which sequence you're talking about.
Precisely. It highlights the importance of specificity. And what's fascinating about this specific sequence, A000322, with the all ones start, is where it pops up. It's not just an abstract curiosity.
Oh. Where does it show up?
Well, for example, AN plus 2 counts something quite specific in combinatorics. It's the number of words you can make of length n using letters 0, 1, 2, 3, 4, but with a really interesting constraint. Any letter X that you use has to be immediately followed by at least X zeros.
Wow. Okay, so if you use a 2-foot, you need 200 right after it, at minimum.
Exactly. Or a 3-foot needs 3,000. A 0 needs, well, 0 zeros after it, so no constraint there.
That's surprisingly concrete. So these numbers are actually counting possible arrangements under specific rules.
They are. It shows they're not just numbers generated by a formula. They describe real structural patterns.
And there is something else mentioned. Benford's law. That seems unexpected.
It does seem a bit out of left field, doesn't it? Yeah. But yes, apparently, the distribution of the leading digits in A000322 tends to follow Benford's law, where 1 is the most common leading digit, then 2, and so on. Following that logarithmic pattern we see in lots of real-world data, like populations or stock prices or... Exactly. River lengths, physical constants. It's quite pervasive. So finding it here in this sequence defined by such a simple recurrence is, well, it's pretty neat.
It really is. Okay, so we have these two main Pentanacci sequences, A000322 starting with 1s, and A001591 starting with 0s and a 1. They start differently, have different values, but they share that core recurrence. What does that mean for how they grow? Do they approach the same limit, like the golden ratio for Fibonacci?
That's a great question. And the answer is, perhaps surprisingly, yes, they do.
Really? Even with such different starts?
Yes. This goes back to the theory of linear recurrence relations. The long-term behavior, specifically the ratio of successive terms, AN1, that ratio is governed by the largest real root of the characteristic equation of the recurrence.
Okay, and the characteristic equation comes directly from the recurrence itself?
Directly. For the Pentanacci recurrence AN-ANL1 plus M plus AN5, the equation is XU X1 X1 is 0.
Right.
Both A000322 and A001591 share this exact recurrence, so they share the same characteristic equation. Therefore, the ratio of consecutive terms in both sequences will converge to the same value, the positive real root of that polynomial.
Which is the Pentanacci constant.
Which is the Pentanacci constant, yes.
Yeah.
Approximately 1.9659482. The initial conditions influence the early terms heavily, but they don't change that ultimate growth ratio.
That's a really important point. The underlying structure dictates the long-term destiny, so to speak.
In a manner of speaking, yes, it's a fundamental property tied to the recurrence itself.
So wrapping this up, what's the main takeaway for someone studying these sequences? We've got OEIS A000322, the all ones Pentanacci, giving us one specific path. It shows up in combinatorics, follows Benford's law.
And it really drives home that initial conditions define the specific sequence, its identity, its particular properties, and values. But that underlying recurrence relation defines universal properties shared by the whole family, like that limiting constant.
It's a nice illustration of how definitions and structures interact in mathematics.
Definitely. It enriches our understanding. You see the specific and the general playing out together.
Okay, so here's a final thought for you to ponder. We've seen two Pentanacci sequences here defined by the same simple rule but different starts. How many other, maybe undiscovered or less studied sequences are out there, generated by simple recurrences we already know, but with unique starting conditions that might unlock totally different properties or applications we haven't even considered yet.